Okay, hello everybody. Today is the 1st of April. I don't have any good April Fool jokes for you, but we'll carry on as best we can. A couple of housekeeping things. There are 4 student groups, 4 teams that have not signed up for conferences. We've had a couple of I've had a couple of conferences, Carrie has had a couple of conferences, but there's still 4 groups that have not signed up. 4 teams that have not signed up. Now, if there's a problem with the sign up issues, I think one team did have some issues with trying to sign up, but if there are problems, you need to let us know because we need to be able to get you on track again with that. And then there's another sign up sheet for your presentation slot starting next week. So already next week, there will be 3 talks per day. So that means if we're having 3 talks per day, we can expand the amount of time that each team has for a talk. Wasn't sure how this would all work out, but that means you can have, let's say, 15 minutes to make your presentation and then 5 minutes for questions. And that will give us time to, and then some trade-off time for handing off from one team to the next. But some critical things are that you have to have your talk ready to go and loaded up in a PowerPoint presentation, and you should select one of the team members to share his or her screen with the group. So I will give you permission to share your screen, and then you can share your PowerPoint presentation, and then the different team members will take turns presenting the slides that they have. And you'll have to help whoever is controlling the slides by saying, okay, next slide, that sort of thing, so that you can move through your slides. Are there questions about this? Does everybody understand that you need to sign up for your presentation slot? Can I have a show of hands to indicate that you know that you need to sign up? So please raise your hand if you understand that you have to sign up. All right. And so the conferences with Carrie and me are designed to help you to overcome any shortcomings that might occur in the Milestone 3 preparations. And so we're trying to help you get past those problems. Okay. Another thing that I'll remind you, and I'll put in an announcement, is that part of one of your slides, and you can have this as a conclusion slide. Typically, it's the last slide. Each team needs to prepare 5, 1, 2, 3, 4, 5 multiple choice or true/false questions, which you're going to have provided the answers to, not in terms of ABC or or true or false. You give the answers. The answers are available from the material that you present in your presentation. And those 5 multiple choice questions, some of those, the better questions and the ones that sort of make sense in terms of the overall content, will be part of the final exam. So I hope that's clear. So there'll be, a significant fraction of the questions in the final exam will be drawn from the student presentations and will be prepared by each team. So part of the assignment for Milestone 4 is to prepare 5 multiple choice true/false questions, fill in the blank too, if you like, regarding the material that you tell the class about in your presentation. Is that clear? Okay. All right, today what I want to do is I want to carry on with this discussion of oil production, offshore oil production in the Gulf and elsewhere in the world. And I'm going to sort of be switching from, I'll finish off the the material that I have about natural seeps and how we use satellites to detect the numbers of natural seeps and to try to make some estimates about how much oil they're putting into the ocean. And then we're going to switch from the natural part of the system into the anthropogenic part, offshore oil production for human energy needs, and then offshore oil spills and the way in which they occur and how they affect the environment. And I'm going to be focusing almost exclusively on one oil spill, the BP oil spill. And then Carrie next week will present material over the Taylor Energy site, which is part of her dissertation research. So if you recall, last week we talked about the different kinds of ecosystems that occur at natural oil seeps. These are deep water habitats in the Gulf from water depths of about 500 meters all the way down to the deepest parts of the Gulf of Mexico, which is where oil seeps occur. And so these are lush, biodiverse ecosystems with very high biomass, unusual for the deep sea because the deep sea is largely food limited. But at these places where there's natural hydrocarbons escaping into the marine environment, the carbon in those systems is the basis of a food chain, which includes, which supports high biomass and high biodiversity. And I showed you various pictures and discussed how different kinds of chemosynthesis, chemosynthetic organisms can support these types of ecological settings. And another part of the deep sea environment includes deep sea corals, and this is an example of one of the more common deep sea corals, Lophelia pertosa. And this is a coral, like most other hard coral that occur in the deep ocean. You can see that it's white. It's white. It hasn't been bleached, but it's white because it doesn't have the zooxanthellae, the dinoflagellate symbionts that shallow water corals do. And so there's no pigmentation and hence no coloration, but you still have the same polyp organism that secretes the calcium carbonate skeleton. And these Lophelia reefs can be quite large, and they occur in deep water. Corals survive by filter feeding, and they're prevalent in the Gulf at places where there's carbonate released. And there are a variety of different life forms that exist on these hard grounds. Okay, switching over to thinking about what happens to the oil once it leaves the seabed and floats through the water column up to the surface. I described how when the oil gets to the surface, it spreads out in a thin layer, which, as it gets thinner and thinner, eventually becomes actually invisible in the sense that it doesn't have any color. It's thinner than the thinnest wavelength of visible light, but it nonetheless has an effect on the surface of the ocean. It dampens the capillary waves and creates a bright patch where the place where the oil layer is smoother than the surrounding water because the capillary waves, the little ripples created by wind, have been dampened out. And so those areas appear slick, shiny, and when the sun hits them, the sun reflects off of this layer of floating oil. And so you can see the sun glint pattern created by the layer of oil spreading outward from the source. And I said that we can see these oil slicks from airplanes. You can sort of see them from ships. You sort of can notice the areas, and sometimes you can actually see the bubbles of oil coming to the surface. But if you get it up in an airplane and look down, you can see these long oil slicks. And if you get up in a satellite, you can also look down and see these same sorts of features. So what's happening is that the drops of oil are leaving the bottom, they're rising all the way through the water column, and they're creating these slicks on the surface. And so this is something that, one of the things that discoveries that I helped pioneer early in my career, and I've spent an awful lot of time thinking about how to use this phenomenon to understand better the carbon cycle, or this part of the carbon cycle in the ocean. And now, one of the things that we find, let's see, is that you can image oil slicks not only with optical satellites, satellites that take optical pictures of the bottom, but you can also see them in satellites that use radar as a sensor. I think I talked about this earlier on. And so the radar energy, so these radar satellites are actually shining radar beams down onto the surface of the Earth and in the ocean, and looking at the energy reflected back from that radar image. And in these cases, the oil slicks don't appear bright, they appear dark, but it's the same phenomenon. The radar energy is reflecting off of these oil slicks and creating these patterns. And they have this very distinctive shape where there's an origin, an oil slick origin, and then the oil is coming to the surface here, and then it's drifting down current away from the sites. And I said that there are many things that can create these sorts of slicks or slick-like features on the ocean surface. And it can be difficult to distinguish between an oil slick or a slick feature or target which is created by oil versus one which is created by other processes, sargassum or pollution from a ship, for example. But if you see a persistent pattern of oil slicks at a fixed location, there's a pretty good indication that you're looking at something which has got a natural origin from the seabed. And here's an example of that. So these are radar sat images that are radar satellite images that were collected at a site. And the water depth here is about 800 meters. So it's quite deep. Actually, it's deeper than that. This is about 1,200 meter depth. And these triangles mark, these red triangles mark the location of the origin of 4 separate oil slicks that are coming to the surface. And so this picture was taken, this image, radar image, was taken in 1997. Well, here's a picture taken in 2002, so 5 years later. And, again, once again, and this part marks the location, same location. So this GC767 green dot is the same location in each of these images. And so 5 years later, we see this same pattern. Okay, so there's an indication. There's a oil coming up in the same location. And the thing to notice here is that the 4 OSOs, oil slick origins, are roughly in the same pattern, the same sort of pattern that we see here. The oil slicks themselves are changing direction. And, because we've studied oceanography, we understand why that is. The wind is blowing in a different direction. The currents are slightly different. But the location of the 4 OSOs is relative to each other is roughly the same. And then here we go from 2002 all the way forward to 2006. So 4 years later, we're seeing the same pattern of 4 OSOs. Again, the oil slicks are going off in different directions. And so, and then they're, referenced here, there's a shift in where these oil slick origins are coming to the surface. And again, because we've studied oceanography, we can think that there might be a reason for this. And that reason is the deflection of the bubbles and drops of oil as they're rising through the water column due to currents which are moving them. And you can see an indication of how those currents work. And remember here, these are oil slicks rising up. This is a scale here. This is 500 meters, and you can see that during the rise path through the water, the oil slick has been deflected a little bit from the place where it left the bottom. So if you go straight up here, you can see it's been moved over a couple of 100 meters from its source. Well, that's the same thing that's happening here. These oil slicks are being shifted over. In this case, because it's much deeper water, the deflection is greater because there's a longer rise through the water column in order to be affected by currents. And so this is the indication that this is a natural seep zone in this region. So understanding this, we can look for places in the ocean where we see, in the Gulf, where we see this pattern of oil slick origins, and we can understand that, okay, if we were to dive to the bottom and explore around in this area, we would find natural oil seeps. Okay? And in the case of this site here, if you go down to the bottom, what you would see would be something like this. So here's a pattern on the bottom, and here's a video, which once again is not showing. So there's a stream of bubbles and gas coming out, and it's rising up through the water. And this is a site where we didn't know the exact location of the vents of the sea floor until, well, we had a general idea based on the satellite images. And then when we dived down to the bottom using not a submarine, but a remote operated vehicle, an ROV, we were able to locate these individual plumes of oil and gas coming from the surface, and there were associated tube worms and not so many tube worms, mostly mussels and clams associated with this site. So, this is a case study which demonstrates that this method for finding natural seeps tends to work. All right, what to do with this information? Well, back when I started doing this work, the only way to estimate the size of an oil slick was to manually trace around the dark pattern and sort of measure the area and manually try to determine where its origin was. Well, one of my graduate students, a guy named Oscar Garcia, for his PhD dissertation, he developed an image processing method based on a neural network image processing that was able to distinguish between these natural oil slicks and the surrounding oil sea, the surrounding clean sea. And so instead of taking days, or in some case weeks, to manually trace around the oil slicks, we could run these, take these images and run them through the computer, and in a matter of really just a few minutes, accomplish what it had taken a long time to do before. So having once begun to do that, we could process a great many more images and get a much better handle on where the natural seeps were occurring. And that's useful because if we look over the Gulf of Mexico, there is a very large archive of synthetic aperture radar images covering this region. And there's a lot of reasons for that, but one of the reasons is that oil companies have been, since, based on the discovery that these natural seeps were an indicator of, natural oil slicks were an indicator of places where oil could be found in the deep ocean, oil companies began using satellites as an exploration method for trying to find where they might drill for oil. And so this image here shows the frequency. There are, probably 50 or 60,000 satellite images that have been collected over the Gulf. And so we processed, we were able to acquire basically for free an archive of about 160 to 170 individual SAR images. And this shows the relative frequency of the images that we were able to process. So we used this automated image processing technique to rapidly process and rapidly analyze a large number of satellite images over the Gulf of Mexico. And what we found was, when we did this, that there are some 1,000 natural seep zones in the Gulf. And each one of these little crosses indicates the location of a natural seep zone. But when you look at this, you can see that there's a pattern right away. And lo and behold, the location of the oil seeps corresponds to this region that I showed you in the lecture on Tuesday, where there's a huge accumulation of sediments. And you remember that we said that this sediment accumulation with the organic rich material was part of the prerequisite for hosting hydrocarbon formation. And you can also see that they are located where I said that the salt domes were most prevalent. And so most of the seeps are located in this region. You can also see that there are seeps, not just in the northern Gulf of Mexico in US waters, but also in the southern Gulf of Mexico around Yucatan. This particular region down here is important because this is the location of the Cantarell oil field. And the Cantarell oil field is the place where most of Mexico's offshore oil production comes from. So a lot of the oil which is produced in Mexico and used by Mexicans for their oil and gas and energy needs has come from this Cantarell field. They also have oil production on land, but this has been a very significant part. There's also natural seepage in deep water in the Mexican waters. And so the water depths here are about 3,000 meters. So this is very far offshore and very deep water, but there are natural seeps there. And in here, this is the deepest part of the Gulf of Mexico, and there are natural seeps there. You can also see that when you get over towards Florida and you get over towards the northern part of the Yucatan Peninsula, that the amount of natural seepage really falls off a cliff, and there's almost nothing that would indicate that there's oil in these regions. Why is that? Well, you remember that I talked about the very different geologic origin of the Florida Peninsula and the Yucatan Peninsula, how these were limestone platforms that had migrated up and eventually attached themselves to what's now North America. Well, the absence of sediments and the absence of organic material in these geologic regions means that they are much less productive or much less likely to produce oil and gas. And so this distribution of oil, natural oil seeps, indicates the geologic history of conditions that are conducive to producing offshore energy supplies. And this Gulf of Mexico turns out to be an extremely important area globally for the production of oil. And something like 25% or even more, maybe 35% of all the oil produced in North America has historically come from these offshore reserves. Now that situation has changed in the last few years, particularly with the growth in the so-called fracking oil production, where they're using hydraulic fracturing techniques to extract more oil out of older formations that are no longer as productive through conventional methods. But nonetheless, the Gulf of Mexico remains a very important hydrocarbon producing region in terms of supplying human needs. Okay. It's also a matter that the U.S. government, because this is in the Northern Gulf here, this is in within the United States exclusive economic zone, all this oil belongs to the public and is part of our natural heritage. And the government leases these offshore prospects to oil companies. So if an oil company wants to produce oil, they pay a lease fee to the federal government, and that lease fee allows them, it's like basically a rental agreement that allows them to drill for oil and then find oil and produce it and sell it. And that income from oil leasing offshore and also onshore, that has historically been the second largest source of income for the United States, only after the Internal Revenue Service. So this is a very economically important part of the world. Okay. What else can we learn from this satellite investigation? Well, you know, if we take the total picture there and look at the amount of oil, so those images can be used to not only detect the locations where oil is coming to the surface, but also measure the size of the oil slicks. And by making assumptions about how large they are and how thick those floating layers of oil are, they're very, very thin, and I'll talk more about that in a little bit, but we can get some idea of the relative magnitude of seepage. And so this is a way of looking at those same data, but each one of these grid points is a 10 by 10 kilometer square. And then according to the color coding here, we can see that between 8 to up to 15% in the larger areas here of the surface of the ocean, will, on average, was covered with oil produced by natural seepage. Most of the things that we're seeing here are down in less than 1% of the area. So that would say that so if we take these data and we use them to estimate how much oil is coming out, we can get an idea of the total production, and we can also compare different regions. So it turns out that this northwestern portion of the Gulf, so we divide the Gulf into 4 regions: northwest, northeast, southeast, southwest, and not surprisingly, the northwest and the southwest are the most productive areas in terms of natural seepage. The northeast has got some seepage, about 7% of the total, and the southeast rather is just about 0%. And that's significant for us here in Florida because we talk a lot about our concern for not allowing drilling and in order to protect the marine resources. Well, not only we are not allowing it, but there's really not a lot of resource there. So that's a reason to expect that there'll be relatively little oil seepage. All right, what else can we learn from this? Well, we can start to estimate what the magnitude of natural seepage is in terms of how much oil is being put into the water. And back when I first started doing this research, we published a finding that suggested that there was about between 210 and 590,000 barrels of oil per year in the northern Gulf put out. And then working at it for another 10 years or so, or 15 years, we were able to improve our estimate and produce a second estimate, which was very close to the first estimate for the entire Gulf, of about 200,000 to 550,000 barrels of oil per year. That was that's the natural input of oil to the best of our ability. So about 500,000 barrels. A barrel is, for reference, is 42 US gallons. So, what is that? Several million gallons per year is coming out. Well, that's an important number to keep in mind because now we're going to shift gears and we're going to talk about unnatural oil seeps, oil spills. And we're going to be making comparison to the amount of oil released from the BP oil spill, which occurred in 2010. And during that event, the BP oil spill released about 4.1 million barrels of oil. Something like 8 times more oil was released by the BP oil spill into the Gulf compared to the oil released from natural seepage. And so that's one important point. The other important point is that this 500,000 barrels that we see from natural seeps, that occurs, 24/7, 365 days out of the year, spread out across that whole region of the Gulf that I showed you in the map. So the impacts of the oil on the marine ecosystem are very, very diffuse compared to releasing 4.1 million barrels in a very tightly constricted area. This is a way of comparing, the so-called pollution from natural seepage to the pollution created by an oil spill. Okay. So what I want to do now is start talking about the history of oil production offshore. And of course, we said that, coastal regions are a good place to produce oil. And so oil producers in the early days, would build their platforms right close to the shore. And then they realized, well, we could go out on piers and put oil platforms offshore and find more reservoirs. And so this is a picture. This is taken in the 1940s. This is actually earlier than that. This is from California, and you can see that the oil production, each one of these is a drilling platform, and they drill down and they produce oil from this. And you can see that they're extending that off into deeper waters. So after World War II in the 1940s, they began to actually do away with the pier and just do drilling and production from platforms that were installed in shallow water. And the type of platform, the first type of platform that they used, and one of the most popular ones, and it's still in use today, is something called a jack-up platform. And what a jack-up platform is basically a ship, like this, with 3 giant legs that are raised up and to allow the ship to sail out. And then when the ship is in position, or this rig is in position, then the platform legs are jacked down bit by bit, and slowly the ship is raised up off of the bottom. And so now this oil platform is not floating, but it's resting on these 3 legs. And then what happens is they drill down from the ship, and they drill hundreds, thousands of feet below the mud until they find the oil reservoir like we described, and then oil is produced. And so this was one of the first types of offshore oil platform that was done. But what happened was that as offshore production became more and more important, the reservoirs and the reserves and close to land began to be played out, began to be exhausted. And so the oil companies, in order to keep finding oil, had to go into deeper and deeper water. And in order to get into deeper water, they had to develop different types of technology. And so they began to find technical means for going into deeper water. So here's a picture, and this picture is describing an interesting distinction between oil drilling rigs versus oil productions. And a lot of times you hear about people talking about oil rigs. Well, the oil companies, and the technical term, distinguishes between drilling rigs and production platforms. So an oil rig or a drilling rig is a temporary device that's used to go to a particular place, drill a well, and see whether there's oil to be discovered in the reservoirs below where the oil ship rig is positioned. So these oil drilling rigs gradually became larger and larger. And the first type of drilling rig was the jackup rig, like I showed you. But that technology isn't sufficient, when you get into deep water, because you can't have legs, that are 200 feet long. And so the technology kept developing and developing. And
having watched the entire.
And here is a picture of a more modern drilling rig. And you can see that this is sort of like a giant floating ship with pontoons that extend down under the water. And so this would float, and it would drive out to a location. In this case, it's being transported on another ship, and it just sort of gives you a sense of scale here, how huge these installations are. So under normal circumstances, this drilling platform would drive slowly, like 2 or 3 miles per hour, out to the location. Then they would anchor the drilling rig with a whole array of anchors, and then do the drilling from this platform down into the bottom. And I'll explain how the drilling works in a minute. So this is a drilling rig, and then there are different types of, if they find oil, then they want to put in a permanent platform, which can be in position, and then they'll drill many wells. So the initial sort of exploration well is just there to confirm, oh yeah, we found a good location, and we were tapping into the oil there. And then if they find this good location, they take the temporary drill rig away, and they come back and they build a permanent production platform. So oil platform and oil rig are technically two different things. And so I'd like to use the proper terminology to distinguish between these two things. And it also helps us to understand what we're talking about. Okay, so I talked about a jackup rig. Well, this is another type of oil platform. This is a fixed leg platform. And so this is kind of like the jackup rig, except they build these platform legs. And the platform legs, they can go down 200, 250, 300 meters to the bottom. And they're basically, a giant set of towers that comes up, and then all the production facilities are built into that. And so right here, somewhere in here, is this sort of connector bundle, and that bundle of pipes go down through the water, and then locate the individual wells, and then the wells tap into reservoirs deep below. So this is a fixed leg platform. And then a different type of platform is one that's called a tension leg platform. Well, in a tension leg platform, the platform itself is floating on a series of giant pontoons, giant tanks that are hollow and empty, and they have pumps, and they bilge them out to keep them empty. And the platform balances on top of these four pontoons, and then each one has a series of cables that goes down. So that, with the buoyancy from the floating platform pulling against these cables keeps it under tension and holds the whole thing in place. And so these tension leg platforms can be installed quite deep. And so this is showing a Green Canyon 184. Now this is a site called Bush Hill nearby, and this is the location of this cartoon shows the location of one of the first chemosynthetic communities that we discovered. And so here you can see, a shallow water, a fixed platform on relatively shallow water, and then to be able to have oil production in deeper water, they developed this tension leg production. Well, over time, this has moved into deeper and deeper water. So, here you can see, the evolution, if you like, or development of the technology, starting out in 1978 with the Cognac and Bullwinkle. Bullwinkle was the deepest fixed leg platform ever built, and it was in about 500-meter water depth. And then they started in with these tension leg platforms, and they have gotten deeper and deeper and deeper until present day, when they're already installing these platforms out to about 2,000 meters or greater. Then there's a new type of technology called the floating production facility. And this is essentially a tanker. So, all of these platforms, and I'll show you a graphic to illustrate this in a second, all these platforms have to be connected to land with pipelines so that the oil that's produced can be piped back to shore. Well, in really deep water, these pipelines would have to be very long. And so, one of the solutions is, instead of having a permanently fixed platform, to have a oil tanker. And then you can have an oil tanker that hooks up temporarily to the wellhead at the top of this platform here. And then the oil that's produced from the well is pumped into the tanker, and when the tanker is full, it detaches from this and sails in, and a new tanker comes out and is filled up. So that's the sort of state of the art at present, about 2016. This is the deepest platform, and this was installed already at a depth of about 2,800 meters. This is not in the Gulf of Mexico. I think this was actually offshore Brazil, where they have really deep water production. So deeper and deeper has been the mantra of offshore production. And the result of all this technology has been, construction of an incredible array of pipes and platforms across the Gulf. There are something like 4,000 individual, about 4,500 individual platforms, either currently active or abandoned, no longer in service. And these are connected by an incredible network of pipelines that flow back mostly to Louisiana, Texas, and some go into Mobile. Here's a pipeline that you can't quite see. This pipeline runs from Mobile all the way down to offshore Tampa. And so, this pipeline, supplies, a lot of oil to the Florida region. Okay, and I want to draw your attention to this particular site here. This was the location of the BP Deepwater Horizon oil spill. And that occurred from an oil exploration platform called the Deepwater Horizon. So in 2010, actually starting in 2009, the BP oil company leased a plot of land, plot of water, seabed, from the government. And this was in a region called Mississippi Canyon. And the Mississippi Canyon 852 lease site was leased by BP. And BP drove a ship, hired a drilling platform called the Deepwater Horizon. So that was the mobile platform. And they went to this site. And based on the exploration and the geology that they had performed, they drilled down here expecting to find oil. And so everybody has seen the picture that occurred afterwards. So here is the picture of the Deepwater Horizon. You can just barely see it because of all the smoke and the water and everything. But this is what happened to the Deepwater Horizon. It drilled into a formation. And let me sort of switch over here and you can get a sort of idea of how this transpired. So here is the Deepwater Horizon, and it's been anchored over this site. The water depth of this site is 1,500 meters. And so they start drilling, and then they've drilled down an additional 4,100 meters to where they expect to find oil. when I say drill, what they do is they, when they drill, they have a giant motor which is turning a drill bit, and then they have lengths of pipe, drill pipe. Each length of drill pipe is 20 feet long, and so they're constantly adding new 20-foot sections of drill pipe to the top of the array here, and then 20 feet by 20 feet, the drilling is extending down and down and down, all the way down, to 5,600 meters below sea level, and about 4,100 meters below the seabed. As they get deeper and deeper, they put in casing around this. So they start out with at the seabed here, there's a casing which is about 36 inches in diameter. Okay? And this goes down and down. And by the time they get into the reservoir, they've gotten down to a pipe size which is about 7 inches, 7 to 9 inches, 10 inches in diameter. So a very narrow little pipe is required there. So this was a very difficult well for BP to drill. They hit many formations of very hard, resistant rock. They kept losing drill bits, and they had problem after problem, and they kept getting kickback. So there would be, they would hit these pockets of gas, and these pockets of gas would burp up through the drill thing here. And so it was tremendously difficult. The operators on the ship called this the well from hell. But eventually, in early April of 2010, they broke through and they got into the reservoir that they'd been looking for, and they found an abundant flow of oil. And this was a really nice oil. It was what they call sweet oil, which meant that it had very little sulfur contaminants, and there was also a tremendous amount of natural gas presence with us. So they were very happy. They had found this reservoir of oil, and all the indications were that there were, as many as 2 billion barrels of oil in this reservoir. So this was really good news. But then they made a whole series of fateful decisions, and these decisions, had to be made at the highest level of the BP company. And so the president of BP and the top officials share some blame, almost certainly, for what happened next. So the usual practice when you drill one of these exploration wells and you find your oil is, okay, well, the drill ship is not going to stay permanently in place. It's going to have to go away, and then they're going to have to come back with the platform and drill, install the platform and then drill more wells to get into this site. Well, because this well had been so difficult to drill, and because they had found such a nice reservoir with this first well, the usual practice is that before they leave, they fill the whole well up all the way to the bottom with cement. So they would pour in cement, into this thing, and they'd fill it all the way back up to the mud line to absolutely, totally seal off the reservoir and prevent any oil from escaping. And that's called, shutting in the well. And so cementing in the well. And so that would have been the usual practice to do this. Fateful decision made at the top level of BP was, instead of doing that, let's, here we've got this nice well that's already drilled, and it was really expensive. We're over budget. They spent millions of dollars more, and they took much more time than they had planned. And so they decided, why don't, instead of cementing in the whole well, why don't we just cement in the last couple of 100 feet of the well with a temporary plug, and then when we come back with the production platform, we can just drill out that plug, and then we'll have a well drilled, and we'll save all the money of drilling a new well and all the trouble. So they decided to do that. But this really hadn't been done before. This was not the standard operating procedure. So they had to sort of invent a new technology. And they poured in cement, but they used a sort of nitrogen foam to try to make it's kind of foamed the cement to try to have it fill a larger area. And so they foamed the cement, and they had rods that were supposed to position the plug successfully, that they were in place. Well, I don't know if anybody's seen the movie Deepwater Horizon, but what happened next was really kind of frightening, because once they had that plug in place, they weren't sure if it was really working. The way that they control a well, while it's drilling, so they drill into the well and they hit this reservoir of highly pressurized oil and gas and other fluids. And in order to hold back that pressure from escaping out of the well, they fill the whole well up with something called drilling mud. And this drilling mud it's like mud. It's sort of a very heavy liquid. It's got barium and various cements and muds and clays in it. And so it weighs, water weighs 9 pounds per gallon, and roughly. And the convention of drilling mud is you can have 15-pound mud or 20-pound mud, and that's measuring the weight of the mud per gallon. So if you have 20-pound mud, that means it's twice as heavy as water, and so it tends to hold down. So the column of mud in a well is what stops it blowing out. Well, if you saw the movie, they weren't sure if they had a good seal on this plug that they put in. So to find out, they pumped all the mud out, which was shocking to people. And, they pumped the mud out. And then what happened was all of a sudden the oil and gas started coming up this platform. And of course, as the gas goes up the tube from, this great depth, 5,000 meters below sea level, the gas wants to expand. And of course, it's one of these accelerating things. The more it expands, the faster it goes. The faster it goes, the more it expands. And so this was essentially a cannon shot coming up the well here. And that exploded, the gas and oil exploded up onto the deck of the Deepwater Horizon. The initial explosion and the fire that was created killed 11 people, injured a bunch more. The crew had to abandon, in panic. They had to essentially jump off of the ship into life rafts. The captain of the platform made the decision not to cut it loose from the well, which ended up destroying his ship. The third mate, a woman, recommended that they cut it loose, and the captain overrode her, said, "We're not going to do that." Well, that was a bad mistake, because it ended up destroying the whole thing and killing a bunch of people. Well, okay, this is not impossible that this could occur, and there was something called a blowout preventer. And the blowout preventer is installed at the top of the well here, and this is a giant hydraulic system. This is about 3 stories high, and all of the well goes up through here. All the drill pipe goes through here, and then there are these giant shear ram that's supposed to come in. So this thing is sort of like it's supposed to stop the oil flowing. And so if there's a blowout, these pods are supposed to power, really powerful hydraulic drives, and these drives are supposed to pinch shut and cut off the flow of oil through the pipe. Well, as soon as they realized what the problem was, they tried to activate this blowout preventer. They pushed a button and nothing happened. Well, there were a couple of reasons why nothing happened. First of all, nothing happened because they hadn't changed the batteries on this thing. The blowout preventer that they were using had been in service for several years without being maintained properly. And so literally the batteries were dead that were supposed to operate this. And then the other thing that happened was when the jaws came together, where they were actually able to activate the jaws came together and they hit one of the joints in the pipe. Remember I said the pipe was 20-foot sections. Well, between the sections, there's a pipe joint. And the pipe joint, just by terrible bad luck, happened to fall right within where the blind shear ram was. And so it didn't fully close. And so, this was the result here. And the result, was this particular flow. And so this is a picture taken April 19th and April 20th was when the blowout occurred, and immediately oil started flowing. This picture was taken in 3rd of June, so more than a month later, 6 weeks later. By that time, they had done a whole series of interventions. They'd cut off the risers that go up to the surface, and they had begun making repairs. But you can see from this video what an incredible flow of oil and gas. There's bubbles of gas hydrate in this whole thing. And so this was flowing like this, had been flowing like this for already 6 weeks into the Gulf. And this is further up. You can see that the initial jet of oil coming out of there starts dissipating and spreading out and billowing up. But this whole plume here is oil rising toward the surface. Well, this was a catastrophe. So the oil comes up and it rises up to the surface. Some of the oil dissolves in the water column. Some of it comes to the surface and flares off as gas. Some is burned and forms the oil slick. So these are this is the fate of that oil. And one important thing is that not all of the oil got to the surface. There were deep water plumes that formed. And this is also showing you that the amount of natural gas was quite large. So about almost 40% of the mass of the material coming up was natural gas. And so that natural gas being so abundant was what gave the tremendous pressure to this flow. So that oil came to the surface. And initially, there was a lot of confusion and a lot of deception, really, about how much oil was coming to the surface. In fact, initially, this is a figure showing you how the flow rate estimates changed over time. And so initially, on the 20th, the Coast Guard and BP said, okay, well, we've had this blowout, but we think that the blowout preventer has stopped any oil. We think there's no oil coming to the surface. Well, then they saw the oil slicks on the surface and oil coming up and everything, and they had to sort of revise that. And so they revised it up to about 1,000 barrels a day. And then they started saying that there was more, 10,000. And this is where I got involved, together with the organization SkyTruth. And so I started looking at pictures of the maps of how large the oil slicks were on the surface. And so by using just the data that they published, I didn't believe the numbers that they were saying. So they raised the number up to 5,000 barrels a day. And they said, that's how much oil is coming out, is 5,000 barrels a day. And I looked at the size of the oil slicks that were floating on the surface, and I said, that couldn't possibly be the case. That has to be at least 27,000 barrels per day. So I went on and I tried to, communicate to Exxon, to BP and to other agencies, and I didn't get listened to. So I went to the media. And so for a little while, I was famous as being contradicting all this. Meanwhile, the official story for several weeks continued to be that there was only 5,000 barrels of oil coming out. So there was a period of time when I was very, very nervous about my reputation as a scientist, because I was contradicting all the experts from BP and the experts from the Coast Guard who were saying that the rate of the spill was much smaller. eventually, they agreed to release videos of the oil flow, and these videos were analyzed by other experts, and it soon became clear that the actual rate of the flow, several weeks later, turned out to be in the order of 50 to 60,000 barrels. Well, the eventual official number was that it was 60,000 barrels a day was the sort of worst case. So we don't know exactly. So somewhere between 50 and 60,000 barrels a day was probably the rate of the flow. And so there was this long period of confusion where it was really very difficult to ascertain, and the rates were not properly reported. Well, why did this occur? It occurred, in my opinion, because the scientists really hadn't properly, the experts really hadn't properly learned how to assess the images and the satellite pictures and the aerial pictures that they were seeing of the oil. And in fact, they ignored their own guidelines. And you remember I showed you this picture and I said that the interior here, this is about 5 microns thick, and here this is about 1 micron thick, and here this is less than a micron thick, a few tenths of a micron. Well, this appearance, it's not super precise, but it does give you an accurate assessment of how thick oil is. And so NOAA publishes an open water oil identification job aid, this little diagram here, and this gives some basic ideas about how thick the oil should be. And so what NOAA, the NOAA Field Guide says, so there's different qualifications. Silver sheen is this thinnest layer. That's this silvery means it's thinner than the thinnest wavelength of visible light. Rainbow sheen is in this 0.4 to 5 micron range. Metallic is a little bit thicker. Transition is about 50 microns, and dark oil is somewhere between 100 and 200 microns in thickness. Now, 100 microns, how big is that? Well, a typical human hair is somewhere between 100 and 200 microns in thickness. But, so that sounds like a pretty thin layer, less than a hair's breadth of thickness. But if you have a 1 micron layer that's spread out over a kilometer of water, if you do the arithmetic, and this was a number that I had in my head when I was trying to interpret what the satellite images were saying, 1 micron thick layer over a kilometer of water equals 1 cubic meter of oil, and a cubic meter is about 5 barrels. Based on the evidence that we saw, we kind of thought that the amount of flow had to be much greater. Okay, so this is the field guide that NOAA puts out, and there's actually an international agreement called the Bonn Agreement, which sort of suggests that these should be the guidelines for that. Well, this confusion that occurred came because the Coast Guard uses very different guidelines. So the Coast Guard says that in this guide, you're saying that dark oil is about 200 microns in thickness, but the Coast Guard was using approximations that said that the dark oil was only 2 microns in thickness. And I don't know where this came from, but this was actually published in the U.S. Coast Guard oil spill field operations guide. And so by following these faulty guidelines and ignoring more accurate guidelines, the oil companies initially hugely underestimated the rate of the spill. And that had unfortunate consequences. I think that the oil spill could have been brought under control much more rapidly if they had had an early, more accurate assessment of the rate of the spill. Okay, well, more about what happened. As I said, a lot of the oil didn't flow to the surface. And one of the, this is an AUV, an autonomous underwater vehicle. So this is a robot which goes to the bottom and then drives around. There are, little propellers that push it around, and there are these steering vanes that can control whether it goes up and down. So this AUV was programmed to follow different signals down to the bottom. And one of the things that they looked at was oxygen, dissolved oxygen. And it turned out that there were, and then aromatic hydrocarbons. And so the Sentry AUV was detecting spikes of methane and spikes of aromatic hydrocarbons and little variations in the oxygen concentrations, all of which indicating that not all the oil was reaching the surface. And so and this was also a big controversy because initially the president of BP, Tony Hayward, went on television, I remember, and he said, well, oil floats. So all the oil that's coming out will have floated to the surface, and we don't have to worry about deep water plumes. Well, he was forgetting that if you have a really, really tiny particle of oil on the order of a couple of microns to 100 microns, little hair-thin particle of oil, that's not going to rise to the surface as rapidly as a bigger glob. And it behaves in a sense like little tiny droplets of water that make up a cloud form. So essentially, the oil formed clouds of oil, or the spill formed clouds of oil, which drifted around in these deep sea layers. And a lot of the deep sea organisms that were harmed by these clouds of oil. But then some of the oil did reach the surface. Okay, so that's a little bit about the oil. And let's talk about the response and the assessment. We've got about 10 minutes left, and I'll try to cover all this material that I've got here. So one of the things that came out of all this was the widespread use of something called dispersants. So all this oil came to the surface. It made a big, ugly mess. It was very, concerning at the time. You all were probably a lot younger back in those days, but I'm sure that you remember about the oil spill. What a traumatic thing that was, and how frightening and concerning that was to everybody. And there's a couple of things about that. That the fact that oil spill, that there was a terrible accident, 11 people died, and that was very sad and tragic. But after the initial accident, people weren't dying. It wasn't like COVID. It wasn't like a mass shooting or something like that. But people were still galvanized around this problem of the oil spilling into the Gulf, and everybody just felt terrible about it. And to me, this is a sort of a measure of the way in which people are concerned about the ocean, and concerned about the animals and the ecosystem of the ocean. And so this is sort of like what we call sympathetic trauma. Sympathetic trauma means where you perceive some horrible event happening at a distance, and it affects you personally, even though you yourself are not harmed by this. So I think that the example of the BP oil spill was an example of sympathetic trauma on a large scale, of people being concerned about the impact of the ocean. Well, my involvement in this research didn't end with my little brush with fame. I actually, for a little while, I was famous. I went on television. I was quoted in the New York Times. And there was a period when the whole country was interested in oceanography, and they cared about the loop current and Ekman layers and things like that. So that was a good time to be an oceanographer. But we didn't stop working there. We kept going. We kept trying to understand, how the oil had impacted the environment. One of the big things that happened was they started to get rid of the oil on the surface. They started using something called dispersant, and in particular, a kind of dispersant called Corexit 9500. How does a dispersant work? Well, you've probably had the experience of washing dishes and have a dish pan, and you put a greasy frying pan into your dish pan. Oil comes off of that frying pan and it floats and it forms this gooey layer on the surface of your dish pan, right? Well, when you then take and squirt a little dishwashing soap into that layer, the layer immediately breaks up and goes into the water. And what's happening is that, of course, oil droplets are hydrophobic. They don't mix with oil. They don't mix with water, rather. And that's because the water is a polar molecule and oil is a non-polar molecule. So the way that a dispersant works, and this is the way also that detergents works, is there's a molecule that has one end which is hydrophilic, which attaches to water, and then there's another end of the molecule which is lipophilic, which attaches to the oil or grease. And so if you squirt detergent in, that's what's happening. The one end of the soap sticks to the grease, and the other end sticks to the water, and so that allows the grease to be removed. Well, the same thing can be operated with this powerful detergent. And so Corexit 85 is basically a mixture of Tide, and they mix it with a carrier. So it's kind of, you could make your own dispersant with laundry soap and kerosene. You would get a dispersant. And they sprayed huge quantities, hundreds and hundreds and hundreds of gallons, thousands of gallons per day of this dispersant was sprayed. And so what the dispersant would do is it would form these little lumps with dispersant on the outside and oil droplets on the inside, and that would stop the oil from sticking together and allow it to disperse in the water column. Well, the important thing to notice here is that it's dispersing, it's not disappearing. And, so that comes back. So, but they had to use dispersants. And so this is a picture of dispersants, and this is taken over the wreck site. And this is thick, fresh oil. So you can see there's a big layer of thick, fresh oil here. And then they come and they spray the dispersant, and then the oil all breaks up. And then after the dispersant has had its maximum effect, the oil slicks start forming again. So this whole sequence goes through. And so this was an early test that was performed on the 10th of May. And they did this because the oil layers were so noxious and so thick that the workers on the platform were suffering health effects. And so they had to start using dispersants. But eventually they realized that they decided they could use dispersants over a large scale. Right. I have time to show you a little bit more about the work that we did. And so after the oil spill happened, and starting in about 2012, I was part of a government team that examined and tried to use satellite imaging to discover how widespread the oil was and where the oil actually went. And we used radar satellite images because the radar energy can see through clouds. And so here you see an example of the cloud cover. Actually, I guess I could unhide this. So if you look at a regular photographic image, you're trying to look down on the surface and you can't see through the clouds, and you really can barely see any oil at all. But if you look at with a radar image, you get a very clear picture. The clouds are invisible to the radar, goes right through, and here you can see this big layer of oil. And right here, this radar bright spot is where the Deepwater Horizon platform is located. I think it was down here, I'm not sure. And so, this huge hundreds and hundreds, thousands of square kilometers of ocean surface is the oil slick formed by the discharge from the site here. Well, and this radar sat image is 100 by 100 kilometers to give you a sense of scale. So during the Deepwater Horizon oil spill, there were literally thousands of satellite images collected. Every satellite that could possibly be mobilized was activated, and every image that they could possibly collect was directed at this area. This is the biggest collection of satellite images of the ocean ever undertaken, and I hope ever will be undertaken. Well, my job was to go back and try to analyze these data. And so one of the problems we had was that the oil slick was much larger than any individual oil satellite image could cover. So here's an example of the oil spill, and you can see that the oil slick is extending. This is the satellite picture, and you can see that the oil slick is extending beyond the boundaries of the image. And so the decision that we made, the approach that I suggested for this, was that we should use each individual satellite image as a statistical sample of a larger phenomenon. And you know how statistics work. You take a small sample, subsample of a bigger population, and by examining that subsample, you can estimate what the total population was. And so, in a nutshell, that was the approach we used. It was, in fact, it turned out to be really complicated and difficult computationally, but we carried through. So, here's the going back here. So here's the satellite image. Here's the TCNNA, the neural network processed image. And these little red spots are, the blue is thin oil, and the little red spots are thick oil. And so this was the sample. Well, if we combine the samples, we use the sample statistically, we can project what it was. So here's the thin oil, here's the thick oil in these layers here, and then we can come up with an estimate of what the total oil spill would have been over that whole area. And so that was the approach after about 2 years of work that we ended up taking. So now what I'm going to do is I'm going to show you an animation of the whole oil spill every 12 hours, the estimates that we made, and you'll be able to see how the oil spill progressed. And I'll point out a couple other things they'll go by. These green lines, these green streaks, which you see, these are flight paths of dispersant applications. And so that you would fly over the oil with airplanes, and they would spray this dispersant out. And these are the flight lines. Well, the aerial application of dispersants was probably a total waste of time because they very often missed the oil, and it was only the size of the oil slick was vastly greater than any outline. And in these little circles are places where they burned the oil. Well, the burning of the oil was very effective in getting rid of it, and probably more effective than the aerial dispersant application, except that it created huge clouds of smoke. And that smoke was very detrimental, damaging to whales and porpoises and turtles and everything. All right, so here goes a picture of the spill. And you can see every 12 hours, you can see the burning and the dispersant application. Going forward into June here, and you can see how this is sort of amorphously flowing patch of oil, and then it goes and disappears. And so by August 3rd, all the oil had pretty much dissipated. You couldn't see it. And then this is the cloud of impacts created by oil and gas. All right, so that was oil, and this is the average picture, average footprint of that oil. Okay, I've run out of time. This is a topic which really interests me. We'll talk more about this I guess one take-home message is that the application of dispersants, and they also squirted dispersants into the plume of oil coming out of the bottom. The application of dispersants did in fact decrease the amount of floating oil on the surface, but according to my results, or our results from the team, the effect was to spread that oil over a larger area. So, here is the area of oil-covered water, and you can see that the area of oil-covered water of all thicknesses actually increases after they started putting out dispersants. So this is the volume decreased, but the area increased over time. And so who knows, what's the trade-off? More oil in the water versus less oil spread out over a larger area. personally, I think, you know, you have to evaluate this when you think about the best way to treat Elizabeth. Okay, so I got to stop. We'll be back next week, same place, same time, and Carrie will talk about some of her research, and then we'll start hearing from you, the different teams. And so think about who's going to sign up. And I'll say one other thing: the teams that sign up for the early presentation slots will have the most, we'll cut you slack. We'll view more favorably your presentation. So that should be a motivation to sign up for some of these early spots. All right, goodbye, everybody.